Time to start looking at the antiderivative, or the integral. So, we know how to differentiate powers. Power down front, subtract 1 from the power. If I divide by p, and now if I call it n plus 1 instead of p, I have now made an integral identity. The integral of x to the n, 1 over n plus 1, x to the n plus 1. Also, we have the special case of constants, or zero power. The derivative of a constant is 0, so the antiderivative of 0 is a constant. E to the x, we know that derivative. So we know the antiderivative of e to the x is e to the x. Derivative of sine, that's cosine. So we have another one. Derivative of cosine is minus sine, multiplied by negative. Now it's an integral identity for sine. And tangent, derivative of tangent, secant squared. Let's look at our derivative rule of linearity. Breaking up sum, pulling out constants. So first up, look at sums. Take the derivative of a sum, it's the sum of the derivatives. Hit it with the integral. Integrated derivative, it goes away. And on the other side, it's just the integral of that thing. But f is the integral of f prime. G is the integral of g prime. And I've made a integration rule. The same rule of breaking up sums for derivatives leads to the rule to break up sums for antiderivatives. Pulling out constants, do the same thing. I'll use 3 instead of c. The antiderivative of the derivative, it goes away, and on the other side, it's just the integral. But f is the integral of f prime, and I've generated my pull-out constants rule for antiderivatives. Pull-out constants for the derivative generates a pull-out constants for the antiderivative. Now let's just complete our table of known functions and use our inverses. Derivative of natural log is 1 over x to the minus 1. So the integral goes the other direction. Derivative of inverse sine, 1 over square root 1 minus x squared. Integral goes the other way. Inverse cosine, same thing with a negative. And inverse tangent, 1 over 1 plus x squared. Let's look at the natural log function again, because that means when I integrate a power, I get 1 over n plus 1 next to n plus 1, or natural log, depending on what the power is. If the power is negative 1, natural log. Otherwise, a power. This kind of self-corrects because if n is negative 1, you're dividing by 0. Yeah, you can't do that. The integral of 1 over x is actually natural log absolute value x. To see that, take a derivative. The derivative of natural log absolute value x, 1 over, that's the input, times the derivative of the input, and the derivative of the absolute value function depends on whether you're positive or negative. If your x is positive, it's a line of slope 1. If x is negative, it's a line of slope negative 1. So putting that together, if x is positive, absolute value x is x. If x is negative, absolute value x is negative x, derivative of absolute value negative 1. So in both cases, it's 1 over x. To summarize everything we've done, we have our derivative is linear, led right away to our antiderivative is linear. So we have our one rule, and we have our known elementary functions. Powers, exponential, sine, cosine, tangent, secant squared. The inverse functions, run them through the antiderivative. Powers give me powers or natural log, depending whether the power is -1 or not. Exponentials itself. Sine is minus cosine, cosine sine, secant squared tangent, the inverse sine and cosine functions, and the inverse tangent function. And all of these are plus c.